Hello, everybody, and welcome to the third and the last of our webinar on P2020 and automotive camera image quality. So we are going to start the webinar in a few minutes, waiting for the last participant to log in. So let's start. So today's meeting is about two of the five P2020 KPIs. So this one is about dynamic range and resolution. So it will be divided in two parts. And of course, you'll be free to ask any question you need on the meeting chat anytime. And we will take some time at the end of each part to answer all your questions, first on dynamic range and then on resolution. So let's start the meeting right now. So just an overview of what is IEEE P2020 committee. So Fee here, which will introduce this webinar with me, is part of P2020 committee members, and he will be able to give us more explanation about P2020. So first, Fee, can you tell us more about this committee?
So P2020 is a standardization organism which was made of industrial and researchers that work to establish a set of image quality factors for the automotive cameras. They are taking existing metrics from other standards, and they are adapting them to the automotive sector and specificities.
Okay. And can you tell us more about the release schedule of this new standard?
So there will be a pre-release, hopefully this year, that will allow all people to get access to a first draft of the different KPIs that have been worked on by the group.
Okay. Thank you for all these details. Switch to the next slide. Okay, so I just remind you that here are the key contacts of P2020 officers. Everybody is free to join in the committee and participate. So if you want to participate, please email one of these members, and the participation is free. So let's move on to the first topic of the day. So first, we are going to introduce an overall definition of what is dynamic range, and then we'll jump into what is prescribed by the P2020 current draft for measuring and shooting for dynamic range. So first, Fee, can you please tell us more about what is dynamic range in general?
So dynamic range usually is defined by the ratio between the maximum luminance that you can see or record on the scene and the minimal luminance on it. So basically, when you have a camera that can record n bits, you have 2 to the power of n, ideally in terms of dynamic range. However, due to different elements, the minimum luminance that could be recorded can vary a lot. And so people need to define this value. So first way to see it would be to take the SNR that has a value of 1 to define this minimum luminance. But there might be other ways because it's not robust to flare and other issues like tone mapping and noise reduction.
Okay, and can you let us know what is limiting for dynamic range in a camera?
Sure. When you generate an image through a camera, for instance, here we have the example of a 140 dB chart that is recorded, and then you have the lab environment that will reduces due to some reflections in the seams and other transmissions issues in the atmosphere, for instance. Then you have the optics that will reduces the dynamic range because of the veiling glare. And so this is translated, as you can see, in the lowest part of the graph here, as everything is flattened. Then you have the recording on the sensor, for which you have the saturation, the level, which will reduce the number of photons that you can record. And then on the same sensor, you have the noise, which will reduces the differences between the patches. And in the end, you will get only, for instance, an 80 dB image instead of the 140 dB chart that you had at the beginning of the imaging chain.
Okay, so thank you for this nice overview about the definition of dynamic range. So now let's jump into the topics. So how do P2020 define how the dynamic range should be measured? And first, what is the prescribed chart?
Sure. So P2020 defined first transmissive chart that needs to be at least 140 dB. So to be able to cover from 0.01 lux to 100,000 lux. This chart should have at least pairs of patches here, as you can see, that have a contrast between them of 2 to 1. Also, we should have at least one pair of patch every one stop, which means, for instance, on this 140 dB chart that we have 24 patch pairs. And we need to reduce also the impact of local tone mapping. So to do that, it's important to have a local background around the patch pairs with an average luminance.
Okay, so I believe that you brought with you a prototype of the chart that we have designed at DXOMARK to be able to answer these draft requirements.
Sure, let me show it to you now. So for instance, we have here a prototype of the chart. So if I lower the intensity, you can see some of the patch pair disappearing, and then I can increase again. So it's a transmissive chart with very high dynamic range. So this means that, for instance, on this webcam, you cannot see the whole dynamic. So I'm pushing, for instance, the intensity, and you can see the very dark patch pairs that are appearing now. So, and as you can see, we try to make sure that the bright patches are not symmetrical to the very dark patches, so as not to have a ghost flare that is impacting the measurements on the dark patches.
Okay, thank you for this nice presentation of the charts. So now let's move on to the metrics themselves. So can you tell us more about which metrics is prescribed by the committee?
Yeah, so as I mentioned before, there are issues in terms of defining the boundaries of the dynamic range. So in the P2020, there have been some different bounding metrics that have been defined. The first one is the contrast to noise ratio, also known as CNR. And this one is being used to be able to distinguish between the patch pairs. If you can you can make sure that the patch pairs are more different than the internal noise of each patches. So this is the first metric that has been defined, and it helps to see whether we can really see the contrast between the two patches.
Okay, so how about the second one?
So the second one that has been defined is the tonal contrast gain. it's the ratio between the luminance of the two patches that we are looking at, measured on the chart. In the recorded images over the same luminances, but the real values of luminances. So at some point, this could be seen as a local tone curve transfer function of the system locally for these values of the of luminance.
Okay, so now that we have defined the two bounding metrics, I believe that the P2020 defines two dynamic range metrics, one that is more dedicated for computer vision and the other one for human vision. So can you please introduce them to us, please?
Yeah, sure. So the first one is the contrast detection ratio. This one is, as you mentioned, more dedicated for machine vision applications. So how do we use it? It's used as the CNR thresholding. So we will consider the CNR curves and look at when the CNR is above a certain level. Here we will consider a level of 1, meaning that in dB, so this is showing in dB, for instance, so this means that we're looking at a CNR of 0, in fact, in 0 dB. And this will tells us that if we have a CNR of 1, we are one level above the noise, right, of each patches. And so this is how it is defined. So the CDR in dB will be the differences between the values where we have the maximum and the minimum that are above 1.
Okay. And how about the second matrix that we mentioned?
So the second metric is the visible dynamic range. So this one is, as it is being called, more used by any human vision application. So in that case, we will also add thresholding on the TCG, because this is the second bounding metric that has been considered. And the thresholding is depending on, is a function that will depend on several parameters. And those parameters are fully defined in the draft, so people can refer to the draft after to get a bit more details. But the idea is that for the VDR, we need to consider both CNR above a certain value and TCG above also the thresholds. And in the intersection of both will give us the visible dynamic range. So in a sense, the visible dynamic range will be more limited than the CDR.
Okay, so now that we know what the metrics are, could you tell us more about the lab setup and the shooting protocol?
Sure. So the lab setup, basically what you need to do is take a picture of the chart that we shown before in an otherwise dark lab. And we need to make sure that all emitting sources of light and reflections are fully covered by dark tissues or elements, so as not to have interferences with the measurements. The draft of the P2020 dynamic range allows two options at the moment. First, a single shot capture for the measurement, or a multi-capture with the same exposure, so as to reduce, separate the temporal effects from the normal total effect. So this means that you need to make sure when you do the multiple captures that you are exactly using the same exposure system, so exposure time and analog gains, to make sure that you can average correctly all the images.
Okay, so now I believe we have a pretty clear overview of what P2020 drafts prescribe. So I believe that you already did some measurements in the lab in DXOMARK. So can you please introduce some results that you have?
Yeah, sure. So we did, to validate the measurements, what we did is we used a very well-known camera. So we started with the DSLR, which is well documented at the moment, and the sensor is a linear sensor. So we used a 14-bit full-frame sensor for that, and we made the measurements. So we have here results showing, well, first the image, the resulting image, and we have here the observed versus real relative luminance in the scene for the four channels. And you have here the CNR curve versus the relative luminance, so just as we presented earlier. And you can see that it started about just before -60 dB. We have also the TCG here curve, and we can see that it's a bit larger, going up to -80 dB here. So then if we consider different values, we have extracted directly the computations for you. And you can see, as I mentioned, that the VDR is usually more limited than the CDR. And we're close to, in terms of CDR, to 74, 75 dB, which corresponds to the 14-bit dynamic of the camera.
Okay, and I believe that you already did some measurement. You also did some measurement on a 20-bit camera. Can you show us?
Yeah, we had a 20-bit camera in the lab, so we tried that. And we can see on the CNR that we have the measurements, and we can see that this camera was using several multiple capture to generate a larger dynamic range. And so this is visible here in those different peaks, sorry. And we can see that the dynamic range is more extended than on the other camera anyway, because we have here the curve that starts at -80, while it was around -60 or otherwise. But the TCG remains more or less the same. And so we can see that the CDR is increased compared to the previous results, while the VDR is fairly the same.
Okay, so the measurement you just introduced, it's pretty great, but I believe that you think there are some limitations to these measurements. And can you also tell us how do you plan to cope up with these limitations?
Yeah, so among the group, there have been a lot of measurements. Other people have made also measurements along the DXOMARK, and a lot of people have experienced that the veiling layer of the lens can be a very large limitation for the dynamic range. And also to try and limit that, there have been a lot of discussion inside the group, and what they wanted is really to try to reduce the impact of the bright patches that will generate veiling layer and ghosting over the rest of the patches. And so to do that, the one option at the moment that is being discussed is to reduce the size of the bright patches, and also to remove around those bright patches the surrounding average area, which might not be needed because since the values are very high, the local tone mapping issues might not be as strong as we would need to, as we would see in the very dark environment. So we are working on a new option for the charts, which is what is being shown at the moment.
Okay, so thank you very much for the nice introduction of the dynamic range subgroup work so far. So in a few minutes, we are going to take the question. So you will be able to raise your hand and we will enable the mic, or you can also type the question directly on the chat. So if you have any question, please feel free to ask. So waiting for the first question, maybe we can show again the charts so our audience can have a proper look. Okay. So I believe there is one question. So let me allow your mic.
Yes.
Hello,
Can you hear me?
Alexandra. How are
Hello.
you?
Fine, fine. And you? Can you hear me fine?
Yes, we can hear you.
Yeah. So sorry if the question is not so smart, but the formulas were quite complicated to grasp at first sight. I was wondering. The main issue that we have when we do this measurement is that we have some denoising that will occur, and sometimes the signal to noise ratio of 1 is never reached. So I was wondering if those new ways of measuring dynamic range allow to circumvent this issue somehow.
Yes, the new computation is designed to circumvent the SNR1 issue. So we know that a lot of people were looking at, okay, if we want to look at dynamic range, some considers it as SNR3, for instance. We've seen a lot of documentation about this. But the whole idea of the bounding matrix is to be able to dynamically redefine the bounding matrix for each camera at some point using another way. So the idea is really to make sure that we consider as a for each luminance level the kind of SNR1 limit, while the usual SNR1 is really at the lowest part of the dynamic range and luminance.
Does that answer your question? I think you need to enable your mic again.
I was saying yes. Sorry.
Thank you.
Sorry. Yeah, it got cut. Sorry.
Is there other question in the audience? So waiting for more questions, I remind you that the measure we are able to measure dynamic range using the chart that you just saw. If you are interested to get some measurements or sample measurements on your own camera, please feel free to contact me at sales@dxomark.com or at jsiv@dxomark.com, so we can arrange maybe a measurement session and discuss about how we can help you with dynamic range measurements. Any other question? If not, we will move on to the next topic in a few minutes. So now let's move on to the second topic of this webinar, which is resolution. So here again, we are going to give you an overall definition of resolution. In this case, we are going also to introduce what are the other standard and definition of resolution before telling you more about what is precisely in the P2020 current draft. So let's start. So please, can you tell us overall definition of resolution?
Yeah, so just to start, quick, let's say, reminder of what is resolution. So basically, what are we talking about when we mention resolution? It's the ability to distinguish between two closely spaced objects. We can either see that if the size of the Pons-Break function is too large, then we cannot distinguish the two objects one from another. So this is important, and we need to consider also the number of pixels, so that's the sensor definition, and we need to consider both of them at the same time.
Okay, so I guess there are also some limitations to resolution. So what will limit the resolution of the camera?
Yeah, so if we come back to the how an image is generated, so let's have a look at first, if we image a perfect edge, so this is its profile. We can see it, it's very perfect, very rectangular. Then we have the transmission or in the lab, or then we go through the optics modulation transfer function, the sensor MTF, and what is recorded on the sensor is a smoothed version of the edge that we had, the perfect edge that we had at the beginning. Then we have the image signal processing that will apply some reconstruction and sharpening, and that will generate a final image here. And this final image will have some, will be less smoothed, but will also have some artifacts, as you can see here, which are the ringing artifacts. So this was the analysis, a quick analysis on the spatial domain. And if we look at the frequency domain, so this means that the perfect edge is 100% modulation for every frequencies. And then after going through the lab environment, so imaging through turbulences and other things like that, you have also going through the optics modulation transfer function, and also the sensor. Then you will see that the frequency response is well reduced for the highest frequencies. And then going through the ISP, it will bump some frequencies. And then, as we mentioned, there will be some frequencies that will go higher than 100%, meaning that they are showing the artifacts that I mentioned, like ringing.
Okay, so before we go more into the P2020 current draft content about MTF and resolution measurements, can you tell us more about the other way of measuring MTF?
Yeah, so the first one is, as I mentioned, we were looking at the edge response, the response of the system of an edge. So basically, what people do when they want to measure the modulation transfer function of a lens, they will use something that is like a checkable chart. So it has to have lots of, with high contrast. So we have a lot of edges all over the fields. We have lots of measurements. And this is to be used in linear space. So usually when you have raw images, and you need to make sure that the dark and the bright are not saturated, because if they are saturated, then you will limit the measurement. So the first way to measure the lens, and derived from that, then there have been at least two well-known standards. The first one is the ISO 12233. The latest publication is 2017 on resolution, and that has proposed several charts at the moment for measuring the response of the systems in terms of different frequencies. So they were here the different edges, and now they're proposing also this one with also different edges. And on those ones, so this one was similar to the checkable that we had earlier, meaning that you needed to make sure that you had no saturation either in the bright or in the dark to make the measurements. For this one, the contrast between the dark and the bright has been fairly reduced. and also linearization of the image is now possible through the use of OECF patches here. There were also another proposal for sign SFR, but it's a bit different in terms of processing. On the other side, we had the IEEE P8058 CPIQ proposal, which has its own chart initially, with reduced contrast also between the bright and the dark. And we had OCF patches also to make sure that we can perform the linearization. This was done so as to make sure that we could measure on images after ISP processing.
Okay. So since there were already at least two standards that define resolution, why were there a need to define resolution for automotive camera precisely?
Yeah. So the particularities of P2020 is that the automotive people, they wanted to make sure that they would have consistent measurements for cameras that were from 10 degree to 200 degree field of view. And so this means we needed only one chart and one, the same chart, I mean the same pattern for each measurement point. And so as to make sure that it can be replicated easily and that there's no issues in terms of comparison. Also, as we showed earlier, we needed to make sure that there were gray patches to make sure we can linearize locally the measurement and be sure that we are scene referred. The last part that P2020 wanted was to make sure that the measurements would be done quite fast. And so they requested at some point that people add some markers for automatic detections of the different edges of the chart.
Okay, so let's jump into the content of the current resolution draft of P2020. I have here with me the charts prescribed by P2020 to measure resolution. You can see here on the screen. So, P, can you please give us an overview of these charts and what's the P2020 prescribed?
Yeah, so the charts, I can just do this like this so you can have the focus on the chart. So I'm looking for it. It should be okay right now. So we have 16 patches on the charts for the OECF linearization. We have 4 edges, and we have the 4 markers here. And what also is important is we have a 4:1 contrast between the dark and the bright, which is consistent with the ISO 12233 requirements, which is also followed by the P2020 at the moment.
Okay. Thank you for the presentation of the charts. Let's go back to the PowerPoint. Okay. Okay, so now that we have seen the charts, can you tell us how P2020 prescribed to measure the resolution on this chart?
Yeah, so basically what P2020 does is it will take advantage of existing standards like ISO 12233 2017, adapt it to the requirements that we can find in the cameras in automotive. And what we will do then is what P2020 did is also define a set of KPIs, specific KPIs related to the SFR that are measured.
Okay. So I see that the important point is that the resolution is made the measurement is made in 2 steps. So let's move on to the first step. Could you tell us more about how to do the measurements?
Yeah, so as I mentioned, the first step is to compute the edge-based spatial frequency response. So basically what we need is our slanted edges to make these computations. One important recommendation from P2020 and modification that will be done in the measurement is that initially the slanted edges could only be measured in the horizontal and vertical directions. And now with the modifications made by and followed by the P2020 group, then we can measure in nearly all orientations, sagittal and tangential.
Okay. So can you please detail the measurements?
Yeah. So as I said, the computation is based on the ISO 12233 algorithm, but with some modifications to make sure that we can have wide angles support correctly. So the first modification is to replace the Hamming window during the estimation of the ESF by a Tukey window. So the Tukey window is supposedly also using a parameter, an alpha parameter, and at the moment it's recommended to use a value of 1, but any value could be used at some point as long as it is reported. Why use this window instead of the original Hamming window? As you can see here on the graph, the Hamming window was fairly, I would say, degrading the data while you were going in the field, and a bit too fast. So they decided to go for the Tukey window, which is keeping one value for a longer time. And also, it's what is important is that it's really going to 0, while the Hamming window was not going to 0. So this is the very first important point for this first evaluation, to make sure that the ESF is better analyzed. Then we have also a change in the fitting, because when you are looking at wide-angle cameras, you might have large distortions, and that means that the edges are not straight lines anymore. So to compensate for that, it was introduced to use a 5th-order polynomial fitting instead of the initial linear fitting. So this was for the evaluation of the edge spread function. And then from this edge spread function, we need to derive the edge special frequency response. So then we have also some modification from the algorithms from ISO 12233. The first modification is, again, the use of a Tukey window instead of the Hamming window as previously, so as to make sure that the filtering is cleaner than before. And then we also have what we call a frequency correction, so that we can better take into account the fact that the edges are no longer horizontal or vertical, but now have an angle relative to the rest of the horizontal and the vertical. And so the frequency that needs to be considered needs to be corrected. So that's what has been also added in the standard.
Okay, so thank you for the presentation of the metric. Can you tell us more about the shooting protocol?
Yeah, so P2020 is not only modifying and specifying the algorithm for the computation, but it's also providing recommendations and requirements concerning how you need to take how to capture your images. You need to make sure that you have a very uniform lighting, so over 90% uniformity over the chart that you record. You need to make sure that we have at least 100 pixels for each edges that are usable. And you need to make sure that these 100 pixels are less than 20% of the image field height. If you have fixed focus lenses, then you need to test different focus position. So, I mean, manual focus lenses, you need to test different focus position and report the values for the best focus positions that you find. The exposure needs to make, you need to make sure that the exposure of the chart is fairly defined compared to the edge background reflectors. So, and relative to the dynamic range of the camera. So you need really to set correctly the level of the exposure of the chart to your dynamic range of your camera. The other elements that is important is that the requirements at the moment are measurements at the center and at least in the corners of the image, so as to cover about 50 to be at 75% of image field height. And another strong requirement at some point is to make sure that we reduce the noise influence on this measurement. To do that, it is highly recommended to shoot at least 10 images so as to be able to perform some averages on the KPIs.
Okay, so now that we know how to shoot these charts, using all this image that you have, we will have, so how do we get the final measurements?
Yeah, so basically we have so here's an example of the edge extractions, as we can see. And what is important, for instance, is we will average the data between the two directions that are the same for each field height. So the horizontal direction will be average, and this one will also be average. And for the corners, it will be the same. And what is also important is that you will need to average also all the field height, so that for the same directions.
Okay, so if you remember in the previous slide, we showed that there are two parts of the measurements of the resolution prescribed by P2020. So now we are going to see the other P2020 resolution KPIs.
Yeah, so once you have the measurement itself, I mean the raw measurement, then you need to generate KPIs that are of some values. So P2020 defined several of them, so the special frequency response, SFR, and I will go through all of them so that we can see what's they're really about.
Let's go.
So the first one is the SFR curve itself, so which gives you the modulation for each frequency in the response of the system. So I believe lots of people understand this. So this is fairly easy, and you need to have this SFR curve average for all the images that you shoot. What is but the thing is, it provides a lot of information. It's difficult to know what to understand from a full curve at some point. So some of the KPIs are listed here. So the first one is the SFR10 and the SFR50. So the SFR10 is the spatial frequency for which the MTF modulation, the SFR modulation, sorry, goes down to 10%. And the SFR50 is the frequency for which you have 50% in terms of SFR. Then we can see it the other way around, saying, okay, what is the value of the SFR when we are at half Nyquist, which would be here, or what is the value when we're at quarter Nyquist. And we also can have a look at the maximum SFR value. So in this case, everything is going going down. I mean, it's monotonous. But if you have some specific processing on the image, as I mentioned earlier, when we have, for instance, some image reconstruction with sharpening, then we can get some over sharpening, and then the SFA curve can be higher than 100. And so this is the intent of using this SFA max value. Another interesting KPI is the acutance. So the acutance is the integration of the SFR multiplied by the CSF contrast sensitivity function, which is related to the human vision. So, and this value can give us in one number a rough idea of the how a human will see a lot of details on the image in certain conditions. Other KPIs are related to the previous ones. So this one is the corner variation. So it's really comparing the values that you measured in the different corners and checking, for instance, the SFR50, the maximum value measured in different corners minus the minimum one over the maximum value. Or you can do that also in acutance, and that will give you an idea of the variation of your performances over the field. Okay. Mm-hmm. So those were the different KPIs that were introduced by the P2020.
Okay, so can you please introduce the corner variation of P2020 resolution KPIs?
What, sorry?
Can you please introduce your next slide?
Yeah, so the next slide are some results that we had. So we made measurements using still DSLR just to make sure we had nicely, I would say, calibrated results. Just to make sure that everything was fine and that we could compare that with existing results. So this is an example with the Sony with the Zeiss lens, and we have here the raw image with an extract of the vertical edge and the in red the SFA curve that is measured. So this was measured on the raw, so we can see that there is no specific processing that is applied and no artifacts can be seen. And for all the other KPIs, as I mentioned, we were able to measure them in the corner variance, for instance, in percentage, and we can see that there was a slight variance on the SFA50, and it's also a very small one in the acutance. 4% is not very visible, and we had a full outputs of the different values that we can do.
And does this measurement also work for really wide-angle cameras?
Yeah, the images can be, the chart is compatible with the fisheye lens system, and the measurements will run also on them. So this is examples of chart that were shot on the fisheye lens.
Okay, so I believe this is over with the introduction of P2020 resolution, the resolution KPIs. So in a few minutes, we are going to take any question you have about what has been introduced, even though it's on dynamic range also. So please feel free to raise your hand if you want to ask the question, or ask it directly on the meeting chats. So before we take the first questions, I'd like to introduce all the KPIs that we have introduced in the previous webinars. Please note that we have all the software and hardware available at DXOMARK. If you need to do any tests for your camera, if you want some measurements, sample measurements, you can contact me at sales@dxomark.com. We have also some system for learn, such as the Flare and the Flickr. We have systems that we can learn in US, Europe, and Asia. So if you want to have a try, please feel free to ask. Now that I say that, is there any question about resolution? So we will start with Alexander questions.
Yes, me again, sorry. I was wondering because we have saw that some algorithms, like typically demosaicing algorithms that are very advanced, they can detect the edges and and make nice edges. And for those algorithms, usually we like to use random targets. And here it was not mentioned. Perhaps do you know why we consider like the slanted edge to be enough here for automotive?
Yeah, so there is the P2020 for the resolution. Most of the tests done on resolution and as defined here were oriented for the pre-processing at some point. So before some ISP processing. So just to make sure that we measure camera modules at the same level. That said, there are other, as you mentioned, there are other measurements that can be used to test post ISP. There's been the texture standard, for instance, with the dead leaves or spill coin system, and but it has its drawback at some point. There's been a lot of discussions on that, but also there are also other KPI more oriented towards computer vision, for instance, like CDP that are, or ISNR, or the probability of correct response, that are trying to take into account the reconstruction of the system.
Okay, so for here, in fact, P2020 would recommend to consider the raw image then, if I understand correctly.
Yeah, for the moment, it's more oriented for for systems that are closer to linear response, or that can be linearized easily.
Okay, thanks.
As we mentioned on the chart, you can see that we have the OACF patch. That means that we need to make sure that the linearization is possible.
Got it. Thanks.
Okay, so I believe that there is another question from Leon. I am allowing you to enable your mic. So Leon, please ask your question.
Yes, can you hear me?
Yes.
Okay, yeah, I see this resolution chart. It's actually very complicated because like we only use the 4 slanted edge. Can you explain like what are the patches for?
What do you mean? Oh, so let me go back quickly then.
Yeah, for the resolution chart.
Yeah. So to the definition of the chart itself.
Right.
If my system wants to. So here, the idea is that all those here are the gray patches that are being used for linearization and exposure checking, right? So they're not used for the for the resolution measurements per se directly. They're just used to make sure that we can linearize the data.
Mm-hmm.
And then what is recommended are those, what is not recommended, but what is the requirement is to make sure that the edges that are in red are correct. Then here we have added some additional ones, but they are not mandatory. So the measurements shall be done on those red edges only.
Yeah, thank you. Yeah, you mentioned like the inner, those are smaller patches, they are not mandatory, but what is there any purpose for that?
Well, they are higher, there is a higher contrast on those, so they could be used at some point for additional measurements if needed, but it's not a mandatory in the standard at the moment.
Okay. Yeah, I think another question is related to what you answered just now. I just want to confirm, like, so this measurement, they are all applied to raw image instead of the processed image.
Well, you can apply them on processed image. I mean, if you just generate the linearization, then you can generate the SFR anyway.
Okay.
So it's not that it's not possible. You can do it, but of course, from the physics point of view, as discussed with Alexander earlier, there might be effectively some. The rendering of those edges might be very good, and there might be other elements that are not rendered correctly in the image. The idea is that at the moment, we're just trying to make sure that at least this measurement works in all conditions required for the automotive. And as we mentioned, some of the requirements were the field of view, so that we need a single small chart that we can put everywhere in the field, and that is always the same, so that we can make sure that the measurements are comparable with each other for different lenses, right?
Okay, yeah, thank you very much.
We have 2 minutes left for another question. So if there is no other question, I guess we can wrap up the meeting. If you have further question that you cannot say now, it's still possible for you to send an email to sales@DXOMARK. And also, if you need to request a long system or a measurement service in our facilities, please let me know. So thank you all of you to have followed this webinar. Soon you will receive an email with the slides from the meeting, as well as a recording of this webinar if you need to check some more details. And thank you for attending, and everybody have a nice day. Bye.
Goodbye.